So, we were discussing the response spectrum analysis procedures, and in that procedure we actually have already discussed the overall idea. Today we will focus on its step by step formulation and how we can implement it in a typical code environment. So, this was its overview. The basic idea was that if we know the response spectrum curve for the future earthquake or for the design earthquake, or it can even be for an past earthquake against which you want to perform that analysis. So, if we already have the response spectrum curve, what we can do is that we can take the spectral acceleration values corresponding to all the time periods of all significant vibration modes. So, this spectral acceleration value is giving us an idea about how much acceleration that particular vibration mode in that particular building is going to experience as a result of this application of this earthquake, right. So, that spectral acceleration can be multiplied by the mass of the structure and then by the modal participation factor and then the mode shape itself. This product will give you the total force which your structure is going to you can say experience in that particular mode during the future earthquake, the peak force. So, then that peak force can be distributed along the height and applied as an applied loading to calculate the responses corresponding to that mode contribution, and then we can repeat that process for second mode, third mode, right, and finally calculate the responses. All the responses are then combined to get the approximate peak response, total response, and one of the common way of combining these modal responses is SRSS, square root of the sum of squares, SRSS. So, we scale all the individual modal quantities, then sum them and take their square root, and obviously the final response which we get, the force and displacement, we have to divide with R over I, just like the ELF procedure, because we are applying that earthquake force to a linear structural model, and we want to invoke the same concept as in the ELF procedure to use R and I. So, initially the structure would have followed this straight line, this line up till this elastic base shear, this point, right. But when we divide the applied force by an R factor, we are actually forcing our structure to follow this blue line or non-linear line, right. So, the R factor is applied on all the responses. Finally, the CD factor should also be applied to all the displacement responses, right. Just like ELF, all the displacement and drifts should be applied with a CD factor. So, that is that R, CD and omega factor, also I factor, they are common for all three seismic analysis procedures in the linear domain: ELF procedure, RSA and then time history, right. So, these three will be applied to all three procedures. So, now let us break it up in a step by step manner. So, let me step by step explain the RSA procedure when it is applied to any n-story building with a symmetrical plan about both orthogonal axes, and the seismic loading is also applied along an axis of symmetry. So, it is not applied at any angle from the axis of symmetry, right. So, if your structure is regular and if it is symmetric about x and y axis, let us say this is plan view and this is x axis, this is y axis, and the response spectrum is also applied in either x direction or in y direction, not at any angle, then you can follow the step by step procedure to calculate the responses of any building using RSA procedure. So, as we have discussed in that overall slide also, that first step is the determination of natural frequencies and the natural mode shape vectors. So, we need to perform eigenvalue analysis or Ritz analysis to calculate these natural frequencies and natural mode shapes. So, calculation of omega n for any nth mode and calculation of phi n for any nth mode is the very first step, and obviously for performing this step 1 you need the M matrix and K matrix of the structure, which means that you need a computer model, right. A computer model sophisticated enough to provide all the entries in the mass matrix and K matrix. So, from structure side in this step 1, M and K will be your input and eigenvalue analysis will be performed and your omega and phi will be your output, right. So, in ETABS for example, you know how to perform modal analysis and how to extract first few natural frequencies and first few mode shape vectors. Once you calculate omega and phi, you can also calculate another modal property which is called modal participation factor, which is denoted by this symbol gamma, and it can also be calculated for each mode, right. And it for its theoretical detail and concept, I refer you to my detailed video playlist on the RSA procedure, but for now just see here that it is one factor, constant quantity, which can be calculated for each mode, and its definition mathematically is that for any nth mode, gamma n will be that mode shape vector multiplied by the mass matrix transpose of that mode shape vector multiplied by the mass matrix multiplied by an influence vector. Influence vector tells us that which degree of freedom is in the direction of applied loading and which is not. So, if all of your degrees of freedom are in the direction of applied response spectrum, then this I1 vector will be comprising of all entries as 1, right, otherwise 0. So, for a 5-story building, if I say that I vector is 1 1 1 0 0, which means that first 3 degrees of freedom are in the direction of applied loading and the other 2 are not, right. So, if we are applying response spectrum in horizontal direction, then first 3 degrees of freedom may be in horizontal direction and the other 2 may be in vertical direction, which will not be affected by the horizontal loading, right. So, this whole product phi n transpose m times influence vector divided by phi n transpose again times mass matrix times phi n again. This ratio is actually is the gamma factor, right. This bottom thing is actually modal mass mu, the same thing which I described in the mode superposition method. So, this is modal mass at the denominator and this numerator is again a function of phi and m. This thing is sometimes called as L factor. This numerator is sometimes denoted as Ln. It is also a modal property associated with any nth mode, and the denominator is sometimes defined as mu, denoted as mu factor, modal mass. So, Ln over mu n is actually gamma n. Gamma n is called the modal participation factor and it is used in calculating the equivalent static forces of each mode in the RSA procedure, right. So, for its main derivation from where it actually come, please refer to that second video in the RSA procedure. You will see that while I was solving the governing equation of motion for calculating u of t vector, on one side of the equation we had this ratio. So, we call that ratio as gamma n, right. So, it is not that it is something physically and then we defined it and then denoted it. It is actually came from those calculations. So, we define this ratio as gamma n. So, this is first step in RSA. You calculate the natural frequencies and natural time periods and the associated modal participation factors for all your important modes, and for that you need to have a computer model which is capable of simulating your mass and K matrices. Then second step is the estimation of modal damping ratios xi n for each mode, all significantly participating mode. Generally a 5% damping is assumed, but this 5% is upper limit. It is upper limit prescribed by the code. If you have a high rise building, if you have a steel building, if you have any other special case, then the damping may be less than that number. So, there are special other guidelines which guide you about what xi n you should assume. See, this is an estimation, you cannot exactly calculate it. So, it is an estimation or an assumption based on the type of structural system. So, different guidelines guide us about what xi n we should use for our case and for each mode. Guidelines also guide us that for first mode it should be, let us say 5%, but for second, third mode it can be 3% or 2.5%, right. Third step is for the analysis of new buildings, you should construct the code based design spectrum, the equation prescribed by building code. You construct the spectrum for your site using that equation. You can also go for site specific PSHA, that will directly give you the spectrum for your site. If the analysis is to be performed for a past recorded earthquake, then you should have its response spectrum. So, it can be, the analysis can be performed not only for the new buildings for their design purpose, but also the analysis of buildings or performance evaluation against any other earthquake other than the future code prescribed earthquake. So, it can be a past earthquake also, but you need to construct its response spectrum curve for that purpose. Obviously, the code equation will give you a very smooth spectrum, but the actual spectrum of any past earthquake will be very irregular. It may be like this irregular shape, right. But in any case, you must have this spectrum or construct this spectrum as this step 3, right. So, this is an example here that I have a very regular kind of building, and let us say that I want to apply the response spectrum only in the x direction, right, separately. Let us assume that it occur in a seismic design category B such that the orthogonality effects are not required to be accounted. So, when you perform the analysis in x direction, no need to apply forces in y. So, both direction can be assumed uncoupled, right, separate directions. So, in that case, let us say that I assume that first three modes contribute significantly to my dynamic response, and from fourth onwards I can ignore. So, what I did here is that I extracted from the program first 3 modes in x direction. They were actually not the mode number 1, 2, 3 in the software numbering, they may be like mode number 1, 4 and 7, right. But I extract them, and you will see, by the way, that in the modes list in eTabs, you can simply check the modal mass participation, right, that factor. The highest participation mode in x direction degree of freedom will be your first mode in x direction. The second highest will be second mode in that, and you can confirm by animating also or by plotting their deflected shape. So, if you plot these the center of mass locations, the deflection of center of mass points, that is actually your mode shape, right. So, I normalized that deflection in first mode because it is a shape, it is not actually a deflection. So, I normalize such that the peak number or roof number is 1. So, this gives me my first mode shape, then second mode shape, then third mode shape. So, I extracted them from E tabs, first 3 mode shapes in x direction only. T1, T2, T3, you can see that they are well separated. T1 is 1.4, then T2 is 0.45, around 1/3, and then again 0.2 is your third time period. So, they are well separated. So, this information that whether they are well separated or not is required when you want to select a modal combination rule, SRSS or CQC, right. SRSS is applicable to cases in which the modes are well separated, right, but you can have a building which is all made from reinforced concrete, let us say a nuclear you can say power plant building or any other industrial structure which may not follow that trend. So, the natural frequencies may not be well separated, it may be like 1.4 first mode and then in the same direction 1 second in the second mode, and in the same direction third mode can be 0.8 second. So, which means that modal frequencies or modal time periods are not well separated, they all depend on M and K matrix, right. So, for that case you may go for a more sophisticated modal combination rule, CQC method, and you may not be allowed to use SRSS, right. But for this case they are they follow a general trend because it is a very regular RC building. So, these are my phi1, phi2, phi3 vectors. It is around I think 8-story building, maybe 1, 2, 3, 4, 5, 6, 7, 8, yes, 8-story building. So, I have like you can say 8 entries in my phi vector, and the bottom is fixed support. So, I added 0 at the bottom, right. So, for each from 1 to 8 I have the ordinates for mode 1, 2 and 3, and then I added 0 at the base to show the effect of fixed support. I also calculated this gamma factor for first 3 modes. I simply carried out that multiplication. In this case, since all of my degrees of freedom are in lateral direction only in x direction, because these masses, modal masses and mode shapes, they do not contain any entry corresponding to vertical degree of freedom, right. So, my one vector will be just 1, 1, 1, 1, 1 up till all 8, 9 entries, right. So, no degree of freedom in the y direction or in the vertical direction. So, I carried out that multiplication and I calculate gamma 1 to be 1.3, gamma 2, gamma 3, right. So, this is an example how you will be doing if you want to do it for your building, the RSA procedure, first 2 steps, right. Actually first step. Second step is the xi factor, which is the damping coefficient, you can assume 5%. Then third is take these time periods, actually third is to construct the response spectrum, and then fourth is to calculate modal forces and modal responses. The question is that your gamma 2 is minus, it is negative. So, you mathematically can see directly how will it affect your equivalent static forces. This is the expression for equivalent static forces. This is in the summation form. If I write it in the matrix form or vector form, the equation will become this. Let me write it here. F vector, it is a vector containing all the nodal forces, story forces to be applied for any ith mode, right. This will be equal to gamma I, which is a scalar quantity, times the mass matrix, which is a n by n matrix, which will have all the diagonal entries as the story masses, and all off diagonal term will mostly be 0, and then phi I vector, like this one vector, right, multiplied by SAI, right. So, mass matrix, when it will be multiplied by the phi vector, actually all the diagonal entries will be multiplied by these entries of the phi vector, right. So, it is n by n multiplied by n by 1 vector, right. So, you get an n by 1 vector, which is what? Each story mass is multiplied by the corresponding phi entry. So, the roof mass is multiplied by 1, the other story mass is multiplied by corresponding entry, and you get a vector like this. This vector is multiplied by a product of two scalar quantities. So, gamma I and SAI is just one number, right. So, actually F vector will have the same variation as the mode shape variation, right, because if the story masses are constant, right. If the story masses also have some variation, that effect will be there in the F vector, but assuming that all stories have same mass, the F vector will have the same variation or the direction of forces as the entries in the phi vector. For first mode, all the entries are positive. So, you will get all the forces pushing the building in the same direction at the same time. So, either pushing it in x direction, positive direction, or pushing it in minus x direction, same thing. But in phi 2, the vector which is calculated, some entries are positive, some are negative, some may be again positive. Oh, sorry, this is phi 3, but for phi 2, some are positive and some are negative, right. So, when a minus number is multiplied as gamma I, simply these directions will be reversed, right. So, anyways, you have to apply the response spectrum in positive x as well as in negative x as part of the load combination. Whenever there is an earthquake loading, it is not only unidirectional, it is reversed always, right. So, therefore, these plus sign forces will become minus and minus will become plus, but when you change the direction of the whole loading case, then it will be reversed again. So, practically no effect on the magnitude of the response, right.